Well, thanks, Martin, for that very generous introduction. That's very kind of you. So it was actually 5.5 years ago almost now that CERN announced to the world they discovered a new, what they cautiously described at the time as a new boson, which we've now sort of fairly confidently concluded is at least a Higgs boson. And around that time, suddenly particle physics was all over the news. Brian Cox was wheeled into every television studio to explain to slightly bemused-looking TV anchors what spontaneous symmetry breaking was. And then everyone sort of moved on with their lives and forgot about us. And you might be forgiven for thinking that actually we put our feet up at CERN and just had a holiday for the last 5 years, because there hasn't really been another big breakthrough, at least not one that's got in the news. So what I want to talk to you about today is what we actually have been up to, and particularly there's something it's true there hasn't been a really big breakthrough yet, but just in the last year or two, there have been some really intriguing signs that we might be, and being very cautious about this, we might be about to discover something really quite profound. So this is CERN, which is the European Organization for Nuclear Research, just outside Geneva. It's a sort of the size of a small town. The population of CERN at any one time is about 2,500 people. There are about 7,000 physicists from around the world who are involved in research there. And it's got everything that a small town should have. It's got a restaurant, it's got a post office, travel agents, it's got hotels. So it's a kind of town populated exclusively, though, by particle physicists. So you can kind of imagine what that must be like. This was the scene in the main auditorium at CERN on the 4th of July, 2012. Now, this is as excited as you will ever see particle physicists getting. They were sort of clapping, cheering, people punching the air. One of the people in the crowd described it as being like at a football match. I'm not sure he'd ever been to a football match, but I mean, it was certainly very lively by physics standards. And this is what they were all cheering. It was a bump. So physicists get very excited about bumps. This is, if you want to know what a Higgs boson looks like, this is basically what a Higgs boson looks like. It looks like a bump in a graph. So I'll explain actually what this shows a bit later in the lecture, but really the thing you're looking for here is there's this smoothly falling line, and then there's this little tiny excess here. And that was the smoking gun telling us that there was a new particle that had been found, which over the last few years has been almost certainly confirmed to be the Higgs boson that Peter Higgs predicted back in 1964. So what is a Higgs boson, you might ask? And that's a very reasonable question. So I'm going to very briefly take you on a quick tour of particle physics to try and understand what this thing actually is. So let's start with maybe something slightly more familiar. So this is the periodic table of the chemical elements, which dates back to the 19th century. So at the end of the 19th century, our sort of, the understood theory of what the universe is made from is there are, more than 100 different chemical elements. And thanks to Dalton's atomic theory, what he said was that for every element, hydrogen, helium, lithium, and so on, there was an atom, which was a fundamental, indivisible, indestructible little thing and you had different atoms, one for every element. So that was a sort of Victorian view of the nature of matter. Now, so here's your atom. Then at the turn of the 20th century, so 1897, actually at the Cavendish Laboratory where I work, a particle was discovered, the first elementary particle that we found, called the electron. And that led, over the next few years, to a revision of the structure of the atom. So the atom, as I said before, was thought to be something hard, indestructible, indivisible. When the electron was discovered, that was revised. And we get the model of the atom that we all learn about in school, which is a nucleus which contains most of the mass of the atom, and that's positively charged. And around the atom go these electrons. Now, the periodic table, if you look at it, and the way that the elements were arranged, there are certain patterns in the properties of the different chemical elements. So, for example, if you look at the group 1 elements, they all tend to react in similar ways, and they get more reactive as you go down. But there are clear patterns in the way the elements are arranged, and that was sort of indicative of some deeper structure. And this is the deeper structure. So, essentially, you can explain the properties of all these different elements by different numbers of electrons going around the outside of atoms, and those electrons are what determine the chemical properties of that particular element. Now, this isn't the end of the story. So if we zoom into the nucleus, it was discovered in sort of the early 1930s that the nucleus itself is made of smaller things, and these are called protons and neutrons. So these are smaller particles which make up most of the mass of the atom. The proton is positively charged, the neutron is electrically neutral. They're much, much heavier than electrons. They're about 2,000 times more massive than electrons. Now, this may be where your sort of school physics ended, possibly. But in the 1960s, it was discovered that actually protons and neutrons themselves are not fundamental. They're made of even smaller things, and those smaller things are what we call quarks, or quarks, depending on your taste. So the proton is made of 2 up quarks, which are these red triangles, and 1 down quark. And the neutron is made of 2 down quarks and 1 up quark. And that's it. So that basically says that all of matter, every atom in the universe, everything that we know about, is made up actually of just 3 different elementary particles. So you have the electron, first of all, discovered by J.J. Thomson in Cambridge in 1897. You've got, and the 2 quarks, the up quark and the down quark. So everything that exists is made of just these 3 things. So you are just quarks and electrons arranged in a rather peculiar way, essentially. And these are the first 3 particles of what we call the Standard Model. Now, the Standard Model of particle physics is a rather boring name for something quite extraordinary. It's really the closest we have to a complete description of the universe at the fundamental level. The only thing, well, it misses quite a few things actually, but the main thing that you might be familiar with that it doesn't include is gravity. But other than that, it's got it pretty well pinned down. So you've got these 3 particles that make up all the matter that we're made of. Then there's something else that gets added to this table called a neutrino. Neutrinos are sort of like ghosts. They're these invisible, almost undetectable particles. There are trillions of them going through you right now. They're produced by the sun in vast quantities. They go straight through you, straight through the Earth, and they very, very rarely interact with the ordinary matter that we're made out of. So that's why we're not really that aware of the existence of neutrinos most of the time. So this column of 4 particles makes up what we call the first generation of matter. Now, for some reason, which we do not understand, nature provided us with 2 additional copies of these particles. So there's something called the second generation. And in the second generation, all the particles are exactly the same as in the first generation, except they're more massive and they're unstable. So for example, the electron has a sort of heavy cousin called the muon, which is about 200 times more massive than the electron. And the reason we're not made of muons and there aren't muons hanging around is because if you make a muon, it will very quickly decay into an electron and some neutrinos. So these second generation particles don't hang around very long, they're unstable, but you can make them in high energy collisions like at the LHC, for example. And then then there's a third generation, which is even heavier. So these are 4 by 3, 12 particles are the matter particles. So they make up the kind of solid stuff of the universe, essentially, or at least they would if they weren't all unstable apart from this first column. And we do not know, it is a big mystery, we do not know why there are 2 extra columns in this table. It's a bit like the periodic table in a way, where you have this sort of structure and you can see these patterns, but you don't actually understand yet, back in the 19th century, what underlies this. But there's something suggestive here, something that sort of hints that maybe there's some deeper structure that could explain why we've got this rather peculiar set of matter particles. And I'll come back to that in a little bit. And then the last ingredient in the Standard Model are the force particles. So there are 3 fundamental forces in the Standard Model. Probably the most familiar to you, and one that a lot of important work was done in this building on, is electromagnetism, so by Faraday and Maxwell and various others. So that's the force that causes electrons to stick to the nuclei of atoms. It binds atoms together. It's responsible for chemistry. It's responsible for basically most of the stuff that is important to us. And the particle that transmits the electromagnetic interaction is the photon, the particle of light. So light itself is also an electromagnetic phenomenon. Then there are 3 other particles which you may not have heard of. There's something called the gluon, which is the force particle of something called the strong nuclear force, which is a force that binds quarks together inside the atomic nucleus and binds protons and neutrons together. And it's called a gluon because it glues things, essentially. And then there's 2 rather weird ones called the W and Z particles. And these are particles that transmit a third force, an even weirder one called the weak nuclear force. Now, the weak nuclear force doesn't really bind things together like electromagnetism or the strong force. This force is responsible for causing particles to decay. So when a muon turns into an electron, that happens through the weak force, and I'll talk a bit more about the weak force. It's very important, the weak force. Although we don't really notice it in our daily lives, if it wasn't there, the sun wouldn't be able to fuse hydrogen into helium and there would be no matter in the universe. So it's very important, even though it's not something we're very familiar with. So this is the standard model, and this was the standard model as it had been sort of studied and observed on the 3rd of July 2012. And on the 3rd of July 2012, there was one piece missing, which was this, the Higgs. So, what is this Higgs boson thing, and why is it so important? Well, to understand that, we actually need to ask a slightly deeper question, which is, what do I actually mean by a particle? So you could be forgiven. The way I've described this to you in the last few minutes, you could get the idea that maybe these particles are somehow like little Lego bricks, or they're a bit like the Victorian atoms. They're sort of solid little points that move around and stick together. But actually, that's not what modern particle physics tells us particles are. In fact, particles aren't really what matters at all. Our field is kind of badly named in a sense. What actually we think of as being fundamental are not particles, but fields. So a field, we've all probably, if you've ever held a magnet next to a piece of steel or iron, you've felt the effect of a field. So a field is something that can cause, for example, a force to be exerted over a distance where there's no physical stuff actually causing that force to be exerted. So you can have something, a field can be, so for example, a magnetic field, and that can be strong near a magnet and get weaker as you move further away. Or it can be a gravitational field like the one that the Earth creates around it or the sun creates around it. So we believe that actually in particle physics, every one of these particles has an associated field. So there is a field for the quarks, for the electrons, for the neutrinos, and for all the force particles. And the way we think of these particles are actually as little tiny ripples moving through these fields. So this is a rather nice cartoon by one of my colleagues at Cambridge, David Tong, who's a theoretical physicist. So here you've got your fields, this kind of blue sheet, and then here you've got some particles having a punch-up. So they're kind of these little localized disturbances in these fields. And that's how we think of all matter. So electrons, quarks, everything are just little ripples moving through these cosmic energy fields that fill all of space and are everywhere, which is quite a sort of strange idea, but that's really how we think things are. So coming back to the Higgs, what is the Higgs? Well, the problem existed in the 1960s. When the Standard Model was being put together, it was discovered that if you tried to make the particles in the Standard Model massive, then the theory broke down. It gave you nonsensical answers. So in particular, there was a particular problem with these W and Z particles, these particles that transmit the weak nuclear force. It was known that if they existed, they had to be extremely massive, but if you gave them mass in the theory gave you nonsensical answers. So there had to be some solution to this. And the solution was essentially to invent another field. So just like the other fields that these particles are ripples moving about in, what Peter Higgs essentially said, and actually 5 other colleagues he was working with around about the same time, was imagine that there is, throughout the entire universe, an additional cosmic quantum field. And as these massive particles, these things that we think are massive, move through it, actually, they are imbued with mass by this field. So, for example, the electron, which has a certain mass, what the Higgs mechanism tells us is actually the electron is massless, but by interacting with this cosmic energy field, it acquires the property of mass. So Higgs wrote his paper in early 1964, and he had this idea which was written down with very elegant mathematics, which looks a bit like this. And don't worry, I won't try and explain what this means. And he sent it off to the journal, and his paper was rejected. They basically said, this has nothing whatsoever to do with physics. So Peter Higgs, has nice maths, but nothing to do with reality. So Peter Higgs went back to his paper, and he said, well, I need to connect this with something that could be experimentally measured. And what he added to his paper was actually basically one line that said, if this cosmic energy field that gives mass to all the particles exists, then you should be able to create a ripple or a disturbance in it, which would show up as a new particle. And that ripple in the Higgs field is what we call the Higgs boson. So the thing that gives mass to to the particles we're made of at least, is this field. And the Higgs really is the proof that this field is out there. And that's why finding it was so important. Because the Higgs mechanism, this Higgs process by which the particles get mass, is absolutely fundamental to the standard model. It's kind of like the keystone in an arch. If you take it away, the whole theory just falls in on itself. So it was people were almost kind of convinced, actually, that this thing must be out there. And that's why finding it was so crucial and why everyone got so excited back on that day on the 4th of July. So with the discovery of the Higgs, this completes this standard model of particle physics that I've been telling you about. And this theory is really a kind of incredible achievement, actually, because it can be used to pretty much explain all the physics that we can see around us. So you can use the standard model in principle to describe everything from how a light bulb produces photons to how atoms are fused together inside stars. It's the closest we have, as I said, to a theory of everything. To give you a sense of the power, the predictive power of this theory, this is actually, what I'm going to tell you about now is the best scientific prediction anywhere in science, as far as I'm aware. So here's the electron. Now, the electron, as well as having electric charge, also behaves a bit like it's a tiny bar magnet. So it has a north and south pole, and it gives off a magnetic field. And you can use the standard model to calculate how strong the electron's little bar magnet should be. And you can do this to absolutely fantastic precision. So essentially what you do is you use a supercomputer, you put the theory into the computer, and you calculate, and you get a number that looks like this, 11596521807.3. Plus or minus 2.8 times 10 to the minus 13. So it's a very small number, but very precisely calculated with a very small uncertainty. This is your theoretical prediction. Now, if you do a very, very clever experiment, you can measure this quantity, this very, very tiny quantity, to very high accuracy. And this is what you get, 11596521817.8 plus or minus 7.6. So you can see these numbers agree right down to the last sort of 3 significant figures. And the difference between this number and this number is within the experimental uncertainty on this measurement. So this is a prediction and a measurement accurate to 1 part in a billion. That is really kind of extraordinary. So that tells you that this standard model is definitely onto something. I mean, you don't get this kind of result by accident. So it's a really stunningly successful theory. But it is not without some problems. And these problems are actually what motivated, in part, the building of the Large Hadron Collider in the first place, as well as the discovery of the Higgs, which was really kind of closing the chapter of 20th century physics. What everyone was actually really after, well, a lot of people were after, were answers to some big unsolved questions that the standard model cannot address. Now, I'll go back to this picture. So this is actually an image taken by the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. And what essentially it is where the telescope is pointed at a very dark patch of sky where there are almost no stars, and you wait for a very long time and wait for extremely faint light to build up on the sensor of the telescope. And eventually this is the image that you get. So what you can see in this image, there are actually a few stars. They're the things with the kind of cross twinkly patterns. But everything else pretty much is a galaxy. These are extremely distant galaxies, right sort of almost out to the edge of as far as we can see with telescopes. So, for example, in the center of the image, you can see there's a kind of cluster of galaxies, these kind of blobs. Now, hopefully, you should be able to also see that on this image, there is this smearing pattern. So there's kind of these circular structures arranged around this central cluster of galaxies. And what this smearing is something called gravitational lensing. So this is essentially where light from a distant galaxy travels towards the Earth. Now, thanks to Einstein, we know that gravity doesn't just make matter move in orbits or curves, it also curves space-time, and it will cause light to travel in curved paths. So what's actually happening is, imagine you have if my galaxy is here and the Earth's over there, and there's something heavy in between me, the galaxy, and the Earth over there. As the light leaves the galaxy and travels past this heavy object, it's bent by its gravity and pulled back towards the Earth again. And what you end up getting, it basically acts like a lens, and you end up getting this kind of smeared multiple image of the same galaxy across the whole sky. And this lensing effect can actually therefore be used to work out how much matter there is in the center of this image, because the more gravity, the more mass there is here, the more strongly lensed the light will be, and the more pronounced this effect will be. So what you can do is, if you use this lensing, you can work out how much mass, effectively, there is in the center of this image. And then you can compare that with the visible light that you can see. So we can see there are lots of galaxies here, so there's obviously a very large amount of mass. And what you actually find, though, is that there's a very large discrepancy between the amount of stuff you can see with your optical telescopes and the amount of stuff we know needs to be there to explain this lensing effect. And if you overlay a map of where the matter appears to be in this image from lensing, this is what you get. You get this kind of bluish-purple cloud. This is evidence of something called dark matter, which is essentially some kind of invisible substance, which we don't know what it is, which apparently makes up a very large fraction of the universe. In fact, it's far, far more abundant than the atomic matter, the stuff the Standard Model describes, basically. This dark matter, actually, so you have evidence of dark matter from lensing. You also have evidence of dark matter from simulations like this, which show how the universe formed at the early stages. And essentially, you find that if you want to show how structure in the universe formed, you need dark matter. If you don't put dark matter into your simulations, then you don't get a universe that looks like the one we live in. So this is from the Illustrious simulation group. It's a rather lovely thing. Anyway, you can sort of see galaxies bursting to life and stars turning on and things. Very pretty. But you need the dark matter to make this work and to agree with what we see out there in the sky. And through these kinds of techniques, through lensing, and also by looking at the rotations of stars around galaxies, you can calculate to a fairly high degree of confidence how much dark matter is out there, even though we can't see it. And this is what you get. This is our cosmic pie. And essentially what you see, rather extraordinarily, is this slice here, which I've labeled atoms, which is basically us and everything that we can see when we look up at the sky. So all the galaxies and stars and planets in the universe, and everything the Standard Model describes is just 5% of the total content of the universe. 27% of it, so more than 5 times more of the universe, is made of this invisible dark matter stuff, and we don't know what that is. And then 68% is something called dark energy, and we really don't know what that is. So dark energy is some kind of mysterious, repulsive force that appears to be causing the universe to expand at an ever-increasing rate. So the lesson from this is essentially when you hear the word dark in physics, you should get very suspicious, because it basically means we don't know what we're talking about. And this is really an extraordinary position to find yourself in. You've constructed this, what seems to be this stunningly successful theory over a century with all these clever experiments and clever theories, and then you realize that what you've been describing is actually only a tiny fraction of the total content of the universe. So we're in this extraordinary position of having a theory that works really, really, really well in the very narrow domain in which we've applied it, but tells us basically nothing about 95% of what's out there. So that is definitely a bit of an omission, I suppose you could say, in the Standard Model. There are other problems as well. So we don't know what 95% of the universe is. That's pretty big. Another one is to do with something called antimatter. So that table I showed you at the beginning with all the matter particles, the quarks, the electrons and their cousins and the neutrinos, for every one of these particles, there is a sort of a mirror image particle. And this has been known about for a very long time. It was discovered back in the 1930s. Predicted by someone called Paul Dirac, and then discovered in experiments very shortly afterwards. Every particle in this table, as I said, has a mirror image where all the properties are exactly the same, but the electric charge is the other way around. So, for example, the electron, which is negatively charged, has a positively charged version called the positron, or the anti-electron, depending on what you prefer. And there's muons, anti-muon, there's the up quark and the anti-up quark, the down quark, the anti-down quark, and so on. And these are also part of the Standard Model. We know these things exist. They can be created very reliably in experiments. Their properties are studied. And we know they're out there. And we also know that they are actually indistinguishable from the matter particles, except for their charges being the other way around. Now, this is a bit of a problem, actually, because if you naively apply this sort of understanding of matter-antimatter to the formation of the universe, then this is what happens. So at the Big Bang, you have a huge amount of energy, and that energy is converted into matter and antimatter. And in the Standard Model, whenever you make a matter particle, you also have to make the corresponding antimatter particle. So if you make an electron, you also make with it the positron. And there's this cosmic kind of maelstrom, all these particles, antiparticles being created, and at the same time as they're being created, they're also bumping back into each other and annihilating and turning back into light. So you have this interchange between energy and matter and antimatter. It's boiling and boiling away, and then eventually what happens is the universe expands enough that it cools down low enough that all the matter and antimatter meet up, annihilate, and what you're left with is a cold, dark, and lifeless universe with a few photons whizzing through the infinite blackness. This is what the standard model says the universe should look like. This is what the universe looks like, though. So, copyright Lucasfilm. So the existence of stuff and us and galaxies is a bit of an inconvenience if you're a theorist, because yeah, we don't understand that either. So there must be some kind of process by which you can allow a little bit more matter to survive this cosmic annihilation at the beginning of the universe. And actually, you can work out how big that imbalance has to be. It only has to be very, very tiny. If you look at the sky and count, essentially, the number of photons whizzing through space, there's a rough correspondence between how many photons there are out there and how many particles and antiparticles annihilated at the beginning, because every annihilation, more or less, creates 2 photons. And there are about 1 billion photons for every atom in the universe. And what that tells us is that really we are 1 billionth leftover of a much larger amount of stuff that was there at the beginning. But we don't know how this billionth survived. It shouldn't be there by rights. It should have all been wiped out, and we shouldn't be here. So that's 2 big problems. There's the fact we don't know what 95% of the universe is, and also the theory tells us the universe shouldn't exist. So 2 big problems. I'll come up to a third one. This is one that's probably motivated a lot of theoretical physicists, particularly since Einstein, really, in the 20s and 30s. So this is a problem to do with gravity. Now, gravity, as it turns out, although it feels quite strong, it sticks us to the floor. If you fall out a window, it hurts quite a lot. It's actually terribly weak. It's a fantastically weak force. And this sort of cartoon illustrates that point. So we have the Earth, which is pretty large by any standard, and it's got a gravitational attraction, and it's pulling on this paperclip. I can use a very weak fridge magnet, which is only this big, to pick up that paperclip. So that magnet is overcoming the gravitational attraction of this huge ball of rock, many, many, many times more, larger in terms of mass. So that tells us essentially that the electromagnetic force is way, way, way stronger than gravity. If you had a magnet the size of the Earth, it would be fantastically powerful. You can compare these two. So if we say that electromagnetism has a strength of 1, then gravity's strength is this. It's about 10 to the minus 36, more or less. I won't read that one out. And it's a real puzzle, this. Why is there such a huge hierarchy between gravity and the other forces? So the strong, the weak, and electromagnetism are all way, way, way stronger than gravity. And we don't understand why that is either. So there are lots of problems, potentially, lots of very big problems. And that's what, in large part, the LHC was built to try and solve. Fortunately, though, there are some possible theories out there that could explain some of these. And one of the most popular is an idea called supersymmetry. Now, supersymmetry, the essential idea is to invoke a new kind of symmetry in nature. And it's a symmetry, a rather odd symmetry. So it's not really like this mirror image of antimatter, but it's kind of comparable to it, I suppose. So in supersymmetry, there is a symmetry between the matter particles. So that's things like the quarks and the electrons and the neutrinos, and the force particles, which are the gluons, the photons, and the weak particles, and the Higgs as well. And in supersymmetry, every matter particle gets a force particle partner, and every force particle gets a matter particle partner. So you end up with an extra table of particles that look like this, and they all have really stupid names. So basically, if you want to know what particle's name is in supersymmetry, you add an S to the front of it. So the electron becomes the selectron, the muon becomes the smuon, you get, I think worst of all possibly is the strange squark. Anyway, there should be some kind of commission to name things. I don't know how this happens. They're called sparticles. It sounds very silly the way I've described it. It's very clever, supersymmetry. I don't want to do it down. But supersymmetry is actually, it's sort of, the interest in supersymmetry really began in the 80s, and it's been the most popular extension of the standard model for a very, very long time. And that's because it's incredibly good at solving some of these problems that I've described to you. So, in particular, dark matter. So one of the reasons that supersymmetry is very popular with particle physicists is that often the lightest sparticle is stable, and often it's also electrically neutral. And that's exactly what you want for dark matter. So I said dark matter is invisible, and that's because it doesn't reflect, absorb, or emit light. And things that don't emit, absorb, or reflect light are electrically neutral. So you have an electrically neutral particle that doesn't interact with photons. It could well make up the dark matter in the universe. So that's one reason for liking supersymmetry. Another one, there's a sort of obsession in physics, which is to try to unify things, to simplify complicated phenomena into one sort of single underlying phenomena. And that's true with the forces particularly. And unifying the different forces in physics has been a sort of ongoing quest since Maxwell unified electricity and magnetism in his equations back in the 19th century. So this is a rather confusing graph, unfortunately. I don't know why it's produced this way, but it's upside down. But basically what you've got here, this axis is the strength of the three different forces in the standard model, except they get stronger as you go down rather than going up. But don't worry about that too much. Now, if you do experiments and measure the strength of these forces, what you find, rather curiously, is that the strength of the forces change as you go higher and higher in energy. So that basically means if you have some collider and you bash particles into each other, the harder you hit them into each other, the forces, the strength of these forces alter, essentially. And what you see in the standard model, if you do experiments at higher and higher energies, and these are energies that are way higher than we can actually produce in an experiment, but this is done with theoretical calculations, you find that at some very, very high energy scale, there is a point where these three lines, the electromagnetic force, the weak force, and the strong force, sort of come together a bit, but not quite. If you introduce supersymmetry, these lines meet rather exactly at a particular place, labeled unification. And this suggests that with supersymmetry, these three forces are unified into some single overlying force, which possibly should be called the force. And so that's another reason for liking supersymmetry. It unifies these three apparently disparate forces into one. Actually, we've already unified these two. That's partly what the Higgs is involved in, but never mind about that. It's just a strong force. The other thing that reason to like supersymmetry is that we now double the number of fundamental particles to discover, so people like me are kept employed for a very long time. So that's good. So we like supersymmetry. Another possible theory, so this one tries to explain the weakness of gravity. So there are a number of different versions of this out there. Essentially, these theories posit an extra dimension of space, or sometimes more than one extra dimension of space, as a way of explaining the weakness of gravity. Now, this is apparently an image of what extra dimensions look like. I mean, okay. I'm not so sure, but yeah, apparently it is anyway. So essentially what the idea is, there are some extra directions in which you can move than the up and down, left and right, and forwards and backwards. And the reason that we don't observe them is either because the particles that we're made of are stuck on our three-dimensional sort of space-time, and only certain things can travel through these high dimensions, or it's because these extra dimensions are squished up very tiny, and therefore they're impossible to observe. And the way you explain the weakness of gravity is usually by gravity leaking away into these extra dimensions. So gravity can move through all of the dimensions of space, and therefore it's diluted, whereas electromagnetism is restricted to just live inside these three dimensions that we're familiar with. And if you want to know the results of having extra-dimensional theories like this is what an extra-dimensional theory looks like, according to the Daily Express. So you make a black hole at CERN, and it swallows the entire world. So we haven't seen that yet. Actually, this is what they really look like. So if you make, basically in extra-dimensional theories, often you can make tiny black holes. So this is where you collide your particles with enough energy, they actually collapse a little region of space-time for a tiny moment into a black hole. And the reason we're not really worried about these black holes eating the Earth, like in that rather silly animation, is that according to Hawking's theory, these black holes should almost immediately evaporate. So as soon as they're created, they just go poof. And this is a simulation of one of these black holes disintegrating. So the black hole was here, and it's turned into a whole load of other particles. And they give a very characteristic signature in your detector if you manage to make one of these things, and it's not the whole world falling into a hole. So finding the Higgs was one objective, but finding all these things was a really big part of the reason the LHC was built. And I'm now going to take you on a brief tour of this really extraordinary machine. So this is a map of Europe. We're going to zoom in on Switzerland. This is Lake Geneva. Geneva is just down here, and CERN's about there. If we're going a bit closer, this is an aerial shot from a plane of the Geneva area. So again, you can see Lake Geneva. The city of Geneva is this kind of grey smudge. This long thing here is the airport runway. CERN's over there, and then marked in yellow on the countryside is the route of the Large Hadron Collider. So this is the largest scientific instrument ever built by the human race. By some measures, it's the largest machine ever built. It's 27 kilometers in circumference. It crosses the Swiss-French border twice. It's actually, this yellow line is not there in real life. It's about 100 meters under the ground. The main reason it's underground is actually not because it's dangerous and somehow emits lots of radiation and you need to be shielded from. It's because it would be very expensive to buy 27 kilometers of land to build it on. So it's just below the surface. And the way it works is really quite simple and rather brutal. Over here at CERN, there is a bottle of hydrogen gas, about this large, which is plugged into a 30-meter-long particle accelerator. And that hydrogen is taken out of its canister, it's zapped with an electric field, the hydrogen atoms are ripped apart, so the electrons are ripped off the hydrogen atoms, and you're left with protons, which are just the nuclei of hydrogen atoms. And those are sent down at an accelerator, and then they're sent through a series of accelerators at CERN. So imagine kind of whizzing round a number of different loops. Eventually it goes into this ring called the superproton synchrotron, which back in the 80s was the largest particle accelerator in the world, but now it's just a feeder for the much bigger Large Hadron Collider. So you have a beam of protons that goes, one going this way, one going the other way, and then at 4 points around the ring, these protons are brought into collision inside gigantic three-dimensional digital cameras that take photographs, essentially, of these collisions and try to see if we've created new particles. So if you go underground, this is what you see. Very, very, very long blue tube curving away into the distance. People actually use, there are about 8 access shafts that take you down to the tunnel. People actually use bicycles to get around because the distances are so large. So this blue tube is essentially the world's largest thermos flask. Inside it, there is a bath of liquid helium at minus 271 degrees Celsius, so it's about just above, a bit less than 2 degrees above absolute zero, the lowest possible temperature. And the reason it's very cold is because the way that these particles are steered around the ring are using incredibly powerful magnets. And these magnets are superconducting, which means they have no electrical resistance. And that means you can create extremely strong magnetic fields, but they only work at very, very low temperatures. So the whole machine is cooled down with liquid helium pumped intravenously through this entire ring to make the magnets operate. The engineering challenges in building this are absolutely extraordinary. To give you one fact that I found amazing when I learned it, is that, so you probably learn, maybe you remember from school, if you get a piece of metal and you cool it down, it gets a little bit smaller. It contracts slightly. So you're cooling down a 27-kilometer-long, basically, piece of metal by 271 degrees. And what happens when you do that is the entire machine shrinks by 30 meters in length. So this thing, which has to be aligned to, kind of micron level, has to be able to contract by 30 meters without breaking and without misaligning and without going wrong. And the fact that it works is really amazing. These are the other parts of the machine. So you have a very, very long blue tube, and then at 4 places around the ring, this tunnel opens out into these huge subterranean caverns that are sort of cathedral-sized, and inside these caverns are extraordinary-looking machines like this. This is the compact muon solenoid, which is a strange use of the word compact. So this thing is 15 meters high. So there's a guy in a hard hat for scale just there. It's 25 meters long. It weighs 12,000 tons. It contains enough iron to make 2 Eiffel Towers. Essentially what this thing is an incredibly sophisticated, gigantic 3D digital camera. So what happens is the protons come in through this beam pipe and in one from the other direction. This thing is barrel-shaped, so you imagine it goes off the edge of the image. They collide in the center, you get a whole load of stuff going everywhere, and this detector records those collisions in real time, actually 40 million times every second. This is another one of these. There's 4 of these things. This is the biggest of all. This is Atlas, which is kind of is a good, cool-sounding name. It's a bit of a tortured acronym, so I won't try and tell you what it actually stands for. But essentially, Atlas is even bigger than CMS. This thing is 25 meters high, 40 meters long. It's absolutely huge. If you ever get a chance to go to CERN and get down underground to see these things, which I think is quite difficult, sadly, these days, because it's quite busy there. When I saw them a few years ago, they really are the most amazing things you'll ever see. It's absolutely unbelievable. So Atlas does essentially a very similar job to CMS. They're 2 different experiments, but they work on similar principles, but have completely independent teams and independent technologies, and they're really there to cross-check each other's results. So this is a representative image of what happens when 2 particles collide. Well, it's actually a real image. So this is, what they've got the date on it, I think. So it says 2011, June 25th at 6:30 in the morning. So this is 2 protons meeting. What happens, the reason we're doing these collision experiments is, what we're actually doing is making matter. So you quite often hear particle accelerators or colliders described as atom smashers. And that sort of suggests that what we're doing is breaking atoms apart in order to see what's inside them. But that's not really what we're interested in. People have known what's inside atoms for quite a long time now. What particle colliders actually are ways of making matter that doesn't normally exist in the universe. So you load a huge amount of energy onto each proton. They're given huge speeds. They're going at 99.999991% of the speed of light when they collide. At this point, they're carrying 7,000 times their rest mass energy as kinetic energy. So that means you can make something, essentially, that is 14,000 times heavier than a proton in the collision. They come together, the energy, their kinetic energy is converted into matter, and that's what you're seeing. So you're seeing hundreds of particles being created, and these are not things that are coming from inside the proton. Well, in some cases they are, but a lot of it is stuff that's being made, essentially, out of this kinetic energy. This process of collisions happens 40 million times every second inside all 4 of these experiments, and they run for most of the year, so usually from about April, March, through to just before Christmas. So 24 hours a day with occasional technical stops. So you can get a sense of how many of these collisions are produced. It's absolutely vast, and the data challenges of coping with this rate of collisions is really extraordinary as well. So I'm going to try and briefly now explain to you what that bump was in that graph I showed you at the beginning. So how do you find a Higgs boson? Well, 2 protons collide, and if you're extremely lucky, they will create a Higgs particle. Now, the Higgs particle only lives for a tiny fraction of a second. I think it's something like 10 to the minus 24 seconds. So way, way, way too short to be detected. The Higgs doesn't ever reach the detector. It's created and it disintegrates instantly. Now, one of the ways it can decay is into 2 particles of light. So you get 2 high-energy photons, 2 gamma rays, that fly out from the collision point that came from this Higgs decay. And this is what this event shows. This is from Atlas, again from 2011. So you can see these 2 big bars here are 2 photons. So what an analyst does, a physicist, will say, okay, I'm looking for the Higgs, so go through all these trillions and trillions of collisions and find me all the collisions where there were 2 high-energy photons produced, because they might have come from a Higgs boson. And then you take the energy of those 2 photons, you add them together, and you work out what was the mass of the object which they came from, which was created right at the center of this collision. So you're kind of reconstructing what the Higgs sort of decayed into from the bits that you end up flying through the detector. It's a bit like kind of blowing up a car and trying to work out what kind of car it was from the bits of shrapnel that go flying past, essentially. And what you then do is you take all these pairs of photons, you calculate the energy, the total energy, and you plot it on a graph. And that's all this is. So it's just on the vertical axis, you've got the number of pairs of photons, and on the horizontal axis, you've got the total mass of the object they would have come from. Now, most of the time, when you see 2 photons, they didn't come from a Higgs. They came from something else. So there's lots of ways of making photons. If you bang protons together very hard, you get light. That's what happens. So most of the time, it's just background noise, essentially. And the reason the bump is important is at a certain mass, which is 125 times more or less the mass of the proton, you can see this little excess. And that's because every time you make a Higgs, the Higgs is always the same. A Higgs always has the same mass. So the photons from the Higgs will always add up to the same mass. So you get a little excess at that particular value. So this bump is the sign that this thing is really there. And the thing that really convinced everyone on that day back in July 2012 was that both experiments, Atlas and CMS, both saw a bump in the same place. And that was what everyone when everyone really got excited and started cheering. So that's great. So the LHC switched on for the first time successfully without blowing itself up in 2009. It ran for about 2.5 years until the Higgs announcement came in July 2012. And everyone was very, very happy that day. But then since then, it's been a kind of a string of bad news. This is a story from 2011, actually, even before the Higgs was found, saying certain results were sort of really causing some problems for some of the other theories that we were looking for, particularly supersymmetry. So there were some ideas when the LHC was first switched on that there'd be so many supersymmetric particles, so many sparticles, we wouldn't be able to handle them, and we wouldn't be able to read out the data quickly enough. Actually, what happened is there's not been a sign of these things at all. So there's one from 2011, this is another one from 2015. LHC keeps bruising difficult to kill supersymmetry. popular physics theory running out of hiding places. So you get the idea. And this has really, honestly, been the story, actually, of the last 4.5 years, 5 years now. Since the Higgs was discovered, there's been lots of very important physics being done, don't get me wrong. So, for example, one of the things that Atlas and CMS have been doing is studying the Higgs to try and pin down, is this thing really the standard model Higgs boson that Peter Higgs said should be there, or is it some other more exotic type of thing? Maybe it's a supersymmetric Higgs boson, for example. But all those measurements seem to say it looks very, very like the standard model Higgs boson. And all these other theories, extra dimension, supersymmetry, so far there hasn't been any sign of them. And people, I think, have honestly been getting a little bit anxious about this. There was a big moment of excitement back in 2016, this is the summer of 2016, a new bump turned up. I told you physicists like bumps. So this is a very similar plot to the one I just showed you. It's, again, adding up pairs of photons from inside, in this case, inside the Atlas experiment. And what they saw, again, was something that maybe looked a bit like a bump. And it was at much higher mass this time. So the Higgs mass was about 125 protons, more or less. This thing was about 750 protons. So it was much, much heavier. And this created a huge amount of excitement at the time, possibly a little bit prematurely. So the thing you have to be very careful about, and experimentalists and generally physicists as a whole are very cautious when they see something like this, because there is a certain chance that this kind of bump could just be a fluctuation. It's just sometimes just by random chance, you might happen to get a few more pairs of photons produced at that mass. And it's a bit like rolling a dice, and occasionally you might roll 10 sixes in a row. Even if that's very improbable, if you do enough experiments, you'll get that kind of result once in a while. So maybe this was just a statistical fluctuation, but people did get very excited. This is a graph that shows the excitement of physicists. So this result was announced around the 15th of December, 2015, and this is the number of papers put on the archive over the next 10 days. So you can see just by Christmas Eve, there were almost 100 papers, theoretical papers, trying to explain what this little wobble in a graph was. So there was a huge amount of excitement, and maybe not justified. As it turned out, it wasn't justified, unfortunately. So when Atlas produced the result again with more data, what they found was this little wiggle had disappeared. And essentially it wasn't no one made a mistake. It wasn't that the experiment had got it wrong. Just sometimes by luck or bad luck, sometimes you get a little fluctuation in your graph, and it makes you think briefly that you've discovered something new, but actually you haven't, sadly. But I said there was sort of something interesting happening. And it's actually a series of results that have come out of the experiment that I work on. Now, I can't claim to have been instrumental in these measurements myself, but it's been very exciting being kind of an observer in all of this. So my experiment is called the Large Hadron Collider Beauty Experiment, LHCb. And beauty, beauty stands for a particular type of particle, the B quark, which is actually usually referred to as the bottom quark. But we would rather be known as beauty physicists than bottom physicists. So it's the LHCb beauty experiment. It's not as pretty as Atlas and CMS. It does look a bit like a multicolored toast rack or something, but it's a very, very clever experiment. What LHCb does is really rather different to the other two big guys, Atlas and CMS. So broadly speaking, what Atlas and CMS do are what we call direct searches for new physics, by which I mean they want to bang protons together. So here's your one proton, another proton. They're given lots of energy. They're smashed into each other, and then you make some new, much heavier particle, and you observe it, like the Higgs, for example. And this kind of direct process, the mass of the thing that you can make is limited by how much energy you can put into the collision. So if you remember, Einstein's equation, E equals mc squared. So that tells us that energy and matter are essentially interchangeable. So if you have E energy here and E energy here, then the amount of mass you can make is 2E divided by the speed of light squared. So that tells you how heavy the thing is that you can possibly create. And that's one way of doing physics, and that's how the Higgs was discovered, and that's how a lot of the dark matter searches or the supersymmetry searches work as well. What LHCb does is a bit different. It does measurements which are, broadly speaking, indirect. Now, as a sort of a silly analogy, if you all heard the joke, how do you know an elephant's been in your fridge? Footprints in the butter, yeah, exactly. So if you like, Atlas and CMS are hunting elephants. They're going out into the jungle with a shotgun and trying to find an elephant. Don't do that. And what LHCb are doing actually is trying to find footprints left by elephants. So in a way, they're kind of complementary in a sense that actually, it might be quite, if there aren't very many elephants in the jungle, running across one might be quite rare, but if it leaves footprints all over the place, you might be able to infer there's an elephant out there, although you may not know exactly what type of elephant it is from just looking at its footprints. So that's the sort of an analogy for what we're doing. In terms of the actual physics, the B, as I said, stands for B quark, or bottom quark, or beauty quark. So what we tend to study are the ways that the B quark can decay. So for example, you have this green blob represents a B quark, and let's say it can decay into some other set of particles, some 3 other particles that it will disintegrate into. Now, in the standard model, any decay process where one particle turns into a bunch of particles usually happens via the weak force. So this is the force that mediates these kind of decay processes. So essentially, this particle goes via the weak force into these 3 particles. And just like you could use the standard model to predict very accurately the property of the electron, I showed you that very long number at the beginning, you can also use it to work out how often should a B quark turn into these particular sets of particles. And you can calculate the number often to quite a high level of accuracy. Now, if there exists some other force field, let's say there's a 5th force, let's just make it there. It could be supersymmetry, it could be something else. If that force exists, it can very subtly influence the way these particles decay. It effectively provides another route from the initial state into the final state. So the standard model might be the most kind of the strongest way of getting from your B quark into your set of particles that you're decaying into. But your new physics can also provide a route, and that essentially will slightly enhance the decay rate. So what the kind of game we generally play is we measure these sorts of decay rates. How often does a B quark turn into some set of particles? And we compare that number with what the standard model tells us it ought to be. And if that number disagrees, that can be an indirect hint that some other matter, some other particle, some other force field is coming in and helping that decay along. So it's a sort of it's precision physics. Rather than going out and banging things into each other and looking for some big particle you're creating, you're studying much more abundant. These are still created in collisions. I mean, we're still banging things into each other. But the thing with the B quark is you make billions and billions and billions of them. So you can make very, very precise measurements. And you can detect potentially these very subtle effects caused by new forces that lie beyond the edge of even beyond the energy that the collider can reach, actually. So that's the advantage of indirect measurements, and it's complementary to what ALICE and CMS do. Now, the thing that's been really interesting in the last couple of years are tests of something that sounds a bit arcane, called lepton universality. Now, this is essentially a property of the standard model, which is the leptons, which are the electron, the muon, and the tau, these 3 negatively charged particles, so they're each heavier than the other. The electron's the one we found more than 100 years ago, has a heavier version, the muon, and an even heavier version called the tau. And in the standard model, all 3 of these particles are treated identically. So that means that all the forces interact with these 3 particles pretty much in exactly the same way. And that means if you compare 2 processes that, say, involve electrons and muons, they should have exactly the same rate, more or less. And what we've been looking at LHCb is this process. So you have your B quark, your beauty quark, and it decays via the weak force into a strange quark and 2 electrons. So that's the decay. It's from 1 particle into 3. And the 2 electrons are the crucial bit. They're things to pay attention to. Now, a test of this idea, a test of lepton universality, the fact the standard model treats all of these different versions of the electron the same, that tells us that if we look at a corresponding decay where the B quark turns into a strange quark and 2 muons, which are the heavier versions of the electron, then the rate of this should be exactly the same as the rate of this. And when people started to think about this measurement, there wasn't any really very good reason to think that it was going to produce anything interesting. It was kind of, but it's good to test it. The lepton universality is a sort of a principle of the standard model, so it's good to test these things just to make sure. And what they found was, this is what the standard model says. If you take the number of muon decays and divide it by the number of electron decays, they should be equal. So what the standard model says is this number more or less should be 1 to quite a high level of precision. In 2014, LHCb produced a paper, and this is what they measured. So that's even balance between muons and electrons. They measured 0.75 plus or minus 0.1. So it seemed that there were fewer muon decays than electron decays. Now, this isn't yet anything to get terribly excited about. So if you look at the uncertainty, it's 0.1. This number is only 0.25 away from 1. So that means you only need a kind of, I talked about these fluctuations that can fool you into thinking you found something new. It wouldn't take a very big fluctuation just to send your number down a bit and make it look like you've seen something new and interesting. So there was definite interest in this. It's what we call a sort of 2 sigma effect, which means it's about 2 errors away from what you expect it to be. And there were lots of papers produced in 2014 as a result of this. Then, just this year, the experiment produced an equivalent measurement, so it's with a slightly different set of particles, but basically the same basic thing, so comparing muons and electrons. And this is what they measured. So they measured 0.68 plus or minus 0.08. So this is a little bit further away from 1. It's very close as well to what was measured in 2014. These are 2 independent measurements, though, so they're not using the same data. They're using different sets of data. The fact that they line up like this is quite intriguing, and it's caused some really quite serious interest. So these measurements are, at the moment, the biggest deviations from the standard model anywhere in any experiment that we're aware of. And it's not just these. There are a few other measurements as well of similar sorts of processes that all show slight discrepancies with the standard model. Nothing independently yet to really be sure that it's something new, but they all seem to be lining up in a consistent way. And people are still rightly being very cautious, because it could be, when these measurements are updated in a year or two, that it goes back to 1, that it was just some statistical fluke, or maybe we made a mistake, maybe we've missed some systematic effect in the experiment. Hopefully that's not the case, but that's always possible. So it could be that these things will disappear. But the other possibility is it's not a statistical fluctuation. We haven't messed up. This is actually the sign of something really fundamentally new. And what's interesting is it's something that no one really expected either. It's not supersymmetry, and it's not large extra dimensions. It's something else. And that, in a way, would be even more exciting, because finding something that you really didn't expect is quite often when the biggest breakthroughs happen. So what could this be? Well, there are lots, as I said. I showed you that graph with 100 papers for that previous bump. There are something like 450 papers now out there citing these 2 results from LHCb and a number of other results as well. I'll mention just one, and that's partly because it's a theory that some of my colleagues at the Cavendish Laboratory have been talking about, again, very cautiously. So what their line is, it's extremely unlikely that this is a real effect, because the standard model works so well. If we're going to say that it's broken in some way, that requires really extraordinary evidence. But if this is real, then it could be telling us something really, really fundamental. And it's a question that, in a way, that's been slightly ignored. And it's back to this picture again, this picture of the standard model that we had at the beginning. So I said that there are these 3 generations, the quark and the up and down quark and the electron, and then the charm and the strange quark and the muon, the top and the bottom quark and the tau. And I said we don't know why there are 3 generations. We don't know why there are these particles. Well, one of the possible explanations of this discrepancy could explain this structure. So what we might be on the edge of finding is some extension of the standard model that will, a bit like the discovery of the electron in the 19th century, explain this peculiar periodic table of particles that we currently have at a deeper level. It essentially involves invoking an additional force, a new, very strong force at high energy. And it would also imply some other very interesting things. Apart from possibly being a clue to explain this problem, it would also tell us that the Higgs is not an elementary particle at all. It's not fundamental. It's actually made of other things, other strongly interacting exotic particles. So it would really change fundamentally our understanding of the standard model. And it would be very exciting if this does turn out to be real. Now, people in my experiment are working very hard. Everyone's trying to get into this area, as you can imagine, including me. So I'm starting to sort of do measurements like this, or trying to do measurements like this. There will be updates to these papers quite soon, so probably within the next year, certainly within the next year or so. So the answer to this question should should be coming in very short order. So either we're going to confirm this effect or it's going to disappear and we're all going to get very depressed. But hopefully it's the first and not the second. But it is a very exciting time to be in particle physics. So definitely keep your eyes peeled over the next year or two because we should get an answer either way. Thanks very much.